Hello? Hello? From there? Hello? You're hearing me? Shall I speak again? Yes. Hello? Yeah, it's coming.
Talk by Professor Vaibhav Katewa, and he will be speaking on towards trade-off between security and privacy in linear dynamical system. So Professor Vaibhav Katewa is a faculty at Robert Bosch Center for Cyber Physical System and an associate faculty at the Department of ECE at the IISc Bangalore. Uh, he was a postdoc at the Department of Mechanical Engineering at University of California from 2017 to 2019. He received his PhD from University of Notre Dame in 2016 in electrical engineering. His broad research interests are in analysis and design of dynamical system and networks using tools from control theory, optimization, learnings, and network science. Specific areas of interest include security and privacy for cyber physical system, sparse feedback control design, distributed detection, estimation and control, and network control systems. So before we move on to the talk, we would like to request everyone to subscribe to our Google group for information on future talk. You can also visit our website for more detail from the chat box. Please do check. Finally, we request the online audience to keep your microphone silent for the duration of the talk. And for questions, you can unmute yourself and ask directly or post in the chat box so that we can relay them. Over to you, Professor.
Thanks for the introduction. So Thank you everyone for attending. Today I'll be talking about connections between security and privacy, specifically to linear dynamical systems. So just to start with some motivation, typically these problems are studied differently, and you might have seen security and privacy problems being addressed separately. But what we envision is that there is a fundamental connection between these two problems. So at a broad level, they might look different, but if you look a bit more carefully, you can find some connections between them. And that is what this talk is about. So before we do that, what do I mean by privacy and security? Because there could be multitude of definitions. So here we are focusing specifically on what does privacy mean. So it basically means that if an agent has some private information, then you won't be able to infer those private parameters from the data that you collect. Okay, so that is the inability to infer that private information is what we call it as privacy. And similarly, security is, again, we want to detect some external attacks in the system. Okay, so again, it's an ability to detect these what we call as injection attacks in the system. Okay, so we'll be working with these two definitions of privacy and security. And the system that we will be considering is a discrete time, linear time invariant system. So to start with, I'll give you some motivation, some intuitive understanding on why do these trade-off occur in these systems. So let me ask you a few questions. So let's say if I give you an interconnected system in which there are multiple individual systems and they are sharing information with each other. Okay. So if this information sharing is happening, what do you think? Will the system be more private or will it be less private? Someone wants to. It will be less private, right? Because they are sharing information and people can use that information to infer some private parameters. Okay. Will it be more secure or will it be less secure? Less secure. Okay. Why will it be less secure? So it is less private, right? So think about what do I mean by security here? So security means ability to detect attacks in the system. Okay. So if you are sharing more information amongst the different components in the system, you will be able to better detect the attacks because you have a more visibility of the whole system. And therefore, you can use that information to detect attacks in a better manner. Okay, so that is the first intuition that if the agents share information, they have less privacy and they have more security. Okay, so more information leads to better detection of attacks. So that is the first intuitive reasoning. Let me take a second system. Let's say there is a system which has a large amount of noises present in them. Okay. Again, the same two questions. Do you think such system with large noises, will it be more private or less private? More private, because there is noise in the system, right? So if an attacker on eavesdropper wants to infer some private parameter, then it will be difficult for it to infer that parameter, right? Because of the presence of noises. So it will be more private. Will it be more secure or less secure? Less secure, because the attacker can hide behind those noises also. Okay. So again, you see that the system has more privacy and it has less security. Okay. Let me give you a third example. Suppose there is a system with ambiguity. And what do I mean by ambiguity? That there are multiple initial states that can result in the same output trajectory. So normally in a dynamical system, you start from some initial condition, you apply the control inputs and you get some output trajectories. Okay. So what it says is that you can have multiple initial state that result in the same output. Okay. So that is a property of the system. Now, such a system, will it be more private or less private? More private. Why more private? Right. It can come from multiple initial states, right? So by looking at the trajectory, one cannot distinguish what was the initial state that trajectory was resulting from. Okay, so that inherently implies privacy in the system. Will it be more secure or less secure by that? Less secure, again, because you cannot detect those attacks. Because the attacker can also hide behind this inherent ambiguity present in the system. Okay, so again, this system has more privacy and it has less security. All right. So hopefully these three simple cases convinced you that there is a trade-off between security and privacy. And this is kind of the moral of today's talk. Okay. So normally when we study stories, we have the moral of the story right at the end. So I'm giving you the moral of the story at the beginning itself. So if you don't remember anything else, just this is the main message of this today's talk, that there is a trade-off between security and privacy. So if you want to improve security, that fundamentally implies that system will be less private. So that is the kind of results we have. So these results, this is a slightly older result, which I worked on when I was working as a postdoc. And it was with Fabio Pasqualetti at UC Riverside and Rajshekhar Anguluri, who is currently at ASU. And this work is more recent. It is with my MTech research student, Varki, and he's currently doing PhD at Georgia Tech. Okay. So broadly, I'll be talking about these two different settings. So we'll start with this more recent work, and then I'll continue with the earlier work. So in this first setting, basically, we are looking at a particular notion of privacy, which is called as opacity. So I'll describe what this opacity means. And for the security, again, we have this attack detectability is the notion of security that we are taking here. Okay. So let me motivate what do we mean by opacity in a system. Okay. So again, let me present this example to just motivate the concept. So suppose we have two UAVs which are originating at two different warehouses. Okay. And they are trying to deliver some goods to a particular destination. Let's say this is a home. All right. So now normally what UAVs need to do, they need to transmit their real-time locations. And if they do that, then that can result in privacy. It's a privacy breach because they don't want their locations to be known, right? So what they can do is they can only transmit the average location. So this green line represents an average of the two trajectories. Okay. So to implement privacy, they transmit the average location, not the actual locations. Now, why does it implement privacy? Because they could have started from some alternate positions also, right? And follow these trajectories. And for these trajectories also, they will get the same average location. Okay. So they're getting the same average location from different trajectories. So if someone is observing this average location, that eavesdropper will not be able to tell whether the starting locations were these two warehouses or they were these alternate positions. Okay. So that is kind of an ambiguity in the system because of limited sharing of information. So that is what this point says. An eavesdropper observing the average location cannot estimate what is the origin of the UAVs. So in that sense, the origin is secure, is private in that sense. Okay. But what can happen is that can be presence of undetectable attacks also in the system. Now, what can happen is there is some attacker which, let's say, hacks into both these UAVs. Okay. And it alters the trajectory. So these red lines are altered trajectories. Now, if you look at the average location of these altered trajectories, they're exactly same as the green line. Okay. So what this means is when there is an attack happening and when there is no attack happening, you get the same average location. So in both the cases, you are getting the same information. So using that information, one will not be able to tell whether the attack is happening or not, because the information received is same in both the cases. Okay. So you can see that in this case, there can exist undetectable attacks because there is inherent privacy in the system. Okay. So basically this shows that there is a trade-off between opacity and attack detectability. So now let me go into more formal definitions of the systems, and then we'll see how can we define opacity in a more formal mathematical manner. So this is the system model that we considered. It's a discrete time LTI system. X is the state, U is the input, and Y is the output of the system. And we denote this system by this symbol, okay, gamma. And this is the attack model. So in the attack model, we have this additional inputs. So this B tilde and this U tilde denotes the attack input. Okay. So, and similarly, you have this D tilde and U tilde. So you are modifying your original system to an attacked system, and this is the attack input, right? Now, some other notations, we are talking about secrecy. So you have to define some secret states. So this X naught is the initial state set, and this XS is the secret state set. And the remaining set are called as non-secret states. So if you look at this diagram, you have this whole initial states, and it's divided into secret and non-secret states. A few other notations, this UK is the input sequence until time instant K, and this YX0 UK is the output trajectory resulting from this initial state X naught and from the input sequence UK. Okay. So with these notations, let me motivate what do we exactly mean by opacity. So opacity means the following. So let's say you pick some secret state XS0 from this secret set, okay? And when you apply, you can apply some control input sequence. When you do that, you will observe some output sequence, okay? So opacity implies that no matter what input sequence you apply here, there exists an alternate non-secret state and an alternate non-secret control input such that it results in the same trajectory, okay? So you can think about that for every secret state, there is a proxy non-secret state. And this proxy basically helps us in achieving the same output sequence. If a system satisfies this property, then we'll say that this secret state is opaque with respect to this non-secret set. Okay. Is this clear? Any questions? Okay. So this is the formal definition. We say that a state is opaque with respect to a set if for all possible input sequences there exists an alternate non-secret state and alternate input sequence such that the outputs become equal. Okay. So this is what opacity means. Now we can extend this. This is the opacity of a particular state. We can extend it to an opacity of the set. So if all the states in a set are opaque, we say that the whole set is opaque. Okay. So if you work out the definitions, again, these outputs should be equal. And then due to linearity, you can take this on the left-hand side and you will get this equality. And then we just define this difference as x0 and this difference as u of k. So ultimately, the definition boils down to this, that there should be an initial state and some input sequence such that the output becomes 0. So you should get a 0 output from this initial state and from this control input. So now how do we characterize this opacity? For that, we define this something known as the weakly unobservable subspace. So this subspace is precisely the subspace of all initial conditions such that there exists some control input which makes the output exactly equal to 0. Okay, that is how this subspace is defined. And you see that this condition is exactly the same as what we have seen in the previous slide. So coming back to that, this condition is exactly equivalent to saying that this subspace is not empty. So if this subspace is not empty, then we will have opacity. That is the first result that we have. So a system, there exists an opaque set in a system if and only if this subspace is not empty in that system. All right. So that this is this connection between opacity and this subspace. And this holds true only for linear systems. For example, if you have nonlinear systems, then we won't be able to have this neat result that we have here. So just to, yes. So V gamma is the this weakly unobservable subspace. This one. So this is how it is defined. So it is a set of all initial conditions that result in 0 output. So just to explain this in terms of picture, suppose we have this initial state, okay, and here this blue line is the non-secret state, and everything else in this pink region is a secret state, okay. So in this case, this V gamma, this line is the subspace V gamma, and this is something known, we can do the Kronecker product of this non-secret space with this V gamma subspace. So you get this green strip, all right. Now what happens is that whatever states they intersect with this green strip, they are opaque. So in this case, this right half of this initial conditions, they intersect with the green strip. So all these states will be opaque. And whatever remaining states which do not intersect with this green strip, these remaining state will be transparent. They will not be opaque. So in a system, you can have a portion of the initial conditions which will be opaque and some portion which will be not be opaque. Okay, so this is another condition. You can verify whether a given state is opaque or not using this lemma. So this condition, this initial state is opaque if and only if it lies in this Kronecker sum of these two quantities. Okay, that is what I depicted here. Okay, so we have the condition for existence of opaque sets. We have a condition for verifying whether a particular state is opaque or not. Similarly, we can do it for a set also. We can verify whether a particular set is also opaque or not, again using the same type of relation. So normally they are provided to you, right? Or if you are a system designer, then you might want to design what states you want to keep secret, what states you don't care about being secret. So that is in your hands. So that was all about opacity. Now let's come to security. So as I said, we are talking about the security notion of whether we can be able to detect attacks or not. Okay. So for that, we need to define what is an undetectable attack. So this is how the definition goes. So an attack U tilde is undetectable if this condition holds true. So what does this condition say? That this is the output of initial condition x0 and this attack sequence. This should be equal to another output which results from zero output, control input. Okay. So essentially what we are saying is that whether an attack is present or absent in the system, you get the same output. So if that is the case, then using the output, you won't be able to tell whether there was an attack present or absent in the system. Okay. That is the basic notion of defining an undetectable attack. So here are some notations. This is the set of all undetectable attacks. And this is the set of, so this is the attack sequence, undetectable attack sequence. And this is the set of all undetectable attacks. Okay. Now, if you look closely, this condition is kind of similar to what we saw in the opacity. Okay. So there lies the connection between the two. So again, there's a standard result that there exists an undetectable attack if and only if this weakly anomalous subspace is not empty. Okay, so this is a relation. And earlier we saw that, now we will be able to see the trade-off between the two. So earlier we saw that the opaque set exists when V gamma is not equal to 0. And now we know that undetectable attacks exist if V of gamma tilde is not equal to 0. So notice that slight difference here. This is V gamma and this is V gamma tilde. So gamma is the normal model and gamma tilde is the attack model. Okay. So now you can clearly see the connection. This is the thing. So if there exists an opaque set, that implies that this V gamma is not equal to 0. And if V gamma is not equal to 0, then you can always construct a gamma tilde for which V gamma tilde is also not equal to 0. Okay. So therefore, if you start with an opaque system, ultimately you will lead to a system where you will have undetectable attacks. Okay. So that means lack of security. So opacity here implies lack of security here. Okay. So that is the theorem basically. So if opaque set exists, then there exists an attacked system gamma tilde in which you have undetectable attacks. Okay. And one such set of attack system is given by this condition. So remember, B tilde, D tilde are for attack system and B and D are for the normal system. Okay. So if you can select such attack matrices that satisfy this relation, then it will always have a undetectable attacks. So this is one kind of trade-off that we had shown. Now let us look at a trade-off from a different perspective. And here we will be looking at what is the size of the opaque sets and the size of the undetectable attack sets. Okay. So the idea is the following. So suppose you have initial state. Okay, this x0 is the initial state, and you are expanding this initial state. Okay, so this x02 is larger than x01. And the reason for expanding this state is that so that the secret states can also expand. So remember, secret states are contained in the initial set. Okay, so if the initial set expands, then the secret state can also expand. Okay, so the first question is that if you expand the this x0, will this excess also expand or not? Okay. Will the secret states also become bigger or not? That is the first question. The second question is, will this undetectable attack set, will it also expand or not? Okay, and the answer is yes in both the cases. So we'll show that if you expand the initial state, then both the secret state also expands and the undetectable attack set also expands. So this means that you are getting more privacy because the secret set is expanding, but you are getting less security because this undetectable attack set is also expanding. Okay, so that's what we'll show here. So this first result addresses the first question. It says that if we expand the initial state, then the secret state will also expand. So there exists an XS2 which is larger than XS1 in this case. Okay, and it strictly expands if this condition is it holds true. I'll not parse out this condition, but we have a necessary and sufficient condition. So, and this is the result for the second question. So this result again says that if you expand the initial state, then the undetectable attack set also expands. Okay, so this AU2 is always larger than AU1, larger than or equal to. And it is strictly larger than if this D tilde is square and full rank. So this is a sufficient condition, and this is again a complicated necessary and sufficient condition. Again, I'll not go into the details of this condition. So right now we are assuming they are in Rn. So they need not be, there is no like set in which they need to be contained. No, in the control input, yeah. So Rm, yeah, Rm. Yeah. So M is the size of the control input. So essentially, because of this subspace results, this undetectable attack set will lie in a particular subspace. Okay, so just to summarize, what we have seen is that opacity implies lack of security. Okay, so if you have more privacy in the system, that implies you will have less security. And we have shown that in a couple of different ways in this case. Okay, any questions before we conclude the first part? Now I'll begin the second part. So if there are any questions in this first part. So opacity is a notion of privacy. Correct. Correct. Yeah. So multiple initial states result in same outputs. So that effect is not visible. Okay, so let me move ahead then. So now I'll talk on this work, and I apologize for the change in a drastic change in the slides because this is an older slide deck that I just reused. So let me motivate this problem, and then we'll see what results we have. So here we have an interconnected dynamical system. Okay, so you can think about, we have a smart city, and there's a water network, there's a transportation network, there's an energy network. So normally what happens is that all these different subsystems are operated independently. Okay, but they depend on each other, right? You can imagine the energy network, it provides energy to the transportation and water networks. Similarly, the water network can provide energy to to this energy network also. So there are certain interconnections between them, okay? But normally they are operated independently. So for example, if some attack happens on this energy network, then there is a separate attack monitor that only monitors the energy network, okay? And it will detect attacks only in this energy network, okay? But there are interconnections, okay? So somehow we should be able to use this interconnection to improve the attack detection performance. So that is what we are aiming here. So there is only local attack detection and monitoring using only local information. So again, this attack monitor only uses information from this local system. It does not use information from these other systems. All right. So what we can do is we can share information between these subsystems. All right. So information sharing, as we have seen, it can improve the security performance. It can improve detection performance, but it can also lead to privacy breaches because we are again sharing information. So again, intuitively, if you look at this graph, if you increase the information sharing, then the privacy will go down, but the security will increase. So again, you can see that there's a trade-off here. And one possible solution that you can basically trade off how much information you want to share is to share limited or inaccurate information. Okay, so if you want to have more privacy, then you will share less information or highly inaccurate information. So again, we'll see that the similar kind of trade-off happens in this system as well. So here we are trying to answer three key questions. The first question is, how can these subsystems limit their shared information? So remember, for having privacy, we don't want to share all the information. We want to limit the information in some sense. So that is the privacy mechanism. So how can we design the privacy mechanisms for limiting this information? That is the first question. The second question is, what attack detection procedure can be used? Okay, so that is the second question. How do we detect attacks? And the third question is there a trade-off between these two, similar to what we have seen before? Okay, so we'll be covering these three questions one by one. So let's look at the first question. So here, before we do that, let me present the system model first. So again, we have a discrete time linear time invariant system. So here, xi denotes the state of the ith agent. Okay, so there are multiple agents. Each agent has its own state, and it depends on it. The evolution depends on its own state, as well as the state of all the remaining connected agents. Okay, so for instance, here 1 is connected to 2 and 3. Okay, so this x of -1 will be the states of 2 and 3. And on top of that, there are local attacks in the system. So all the systems, all the agents can have attacks present in them. And we model the attacks as this additive external inputs. And then there is a noise present in the state evolution. Okay. And this is the measurement equation. Again, these are the local measurements, and they depend on the state, and also there is some measurement noise. Now the assumptions are both the noises are Gaussian with zero mean and appropriate covariance matrices. This is the system model that we are working with. We have the local state, we have the interconnected states, we have the attacks, and then we have the local outputs. So now we propose two different ways of implementing privacy or sharing less information. What are those two different ways? The first way is to share limited information. Okay, so notice this yi is the original information, original measurements. We multiply it with a selection matrix. Okay, so for instance, if yi contains, let's say, 2 components, you only select one component out of those 2 components. And then we also add some artificial noise. Okay, again, this noise is being added to implement privacy in the system, because as we have seen before, if you have more noise, you have more privacy. Okay, so these are the two different mechanisms. This is a simple example. So let's say you have this state vector. C is identity, so y is equal to x, and this si is 1, 0. Okay, so you are selecting only the first component, which is this, and you are adding some external noise to that component. Now it's up to you. You can mix and match these two different ways. For instance, you might decide not to add any noise, or you might decide to send all of them but add noise. Okay, so it's in your control. Which mechanism do you want to use and how much do you want to use it? So once we have that, so this is, notice that we have this SH. So this SH means shared information. So you get this actual information, you implement the privacy mechanisms, and then you have this shared information. So this is the vector that the agents will share with the other agents. Okay. So now you can basically time aggregate this. Don't worry too much about this, but essentially we can do a time aggregation, and finally we can represent the vector in this compact form. So we call this as HI, and this everything is noisy here. Okay. So VI are the inherent noises, and this Ni is the artificial noise. So we can combine all of them and call it as Ri. Okay. So we have this simple model, y equal to h times x plus r. That kind of a linear model we have. So now we need to define privacy ordering. So we have defined privacy mechanisms, but how would you say that one mechanism is more private than the other mechanism? So for that, we need some ordering between the different mechanisms. So for that, intuitively, when will you say a mechanism is more private? The first is this mechanisms, MI2 should share less measurement, right? Intuitively, if you are sharing less measurement, then you are more private. Okay, so that is the first criteria. And the second criteria is that estimation error under this second mechanisms should be larger than the first mechanism. Because if the estimation error is larger, that means you are not able to infer the private parameters more accurately, right? So a larger error implies more privacy in the system. So motivated by these two intuitive arguments, we can now mathematically state them. So the first argument is captured by this condition. Okay. So remember, these are the selection matrices. So in some sense, we are saying that the selection matrix in the second mechanism is smaller than the selection matrix in the first mechanism. That means here we are sharing less measurements. Okay, and this is precise condition in terms of the ranges of these selection matrices. Now, mhm. Right. Yeah, that could be another way. So you are saying we compute the unobservable subspace and compare the sizes of those. Right. Yeah, that could be a valid. Right. Yeah. So right. So there is a subtle thing here that in order to have a fair comparison, let's say in one case you are sharing 10 measurements, in the other case you are sharing only 5 measurements, right? So if you compare the estimation errors in these two cases, it's an unfair comparison because the estimation error covariances itself are of different sizes. One is 10 cross 10, one is 5 cross 5. So how do you even compare them, right? So for that, we need separately these two separate things. Okay. So yeah, so to address the second point, we first need to compute the estimation error. Okay. So that's what we will do. So we need to compute the estimate of the state of the agent. So again, we use the standard maximum likelihood estimation. So what we do is typically this estimate is composed of two components. One lies in this range space of HI transpose, and one lies in the null space of HI. Now this part, this can be estimated. okay, although with an error. But this part, it cannot be estimated. So normally what you assume is that the null space of this is empty, so this part vanishes, but that might not be the case every time. Okay, so you have to take care of this part also. So this part cannot be estimated, and this part can be estimated, and the estimation error covariance turns out to be this matrix. Okay. So then what we do is we estimate this first part and compute the estimation error covariances. Now here comes what you were asking. I am not directly comparing sigma E1 with sigma 2 with sigma 1 because there are different sizes. So we'll have to project them on a common space because this Mi1 is operating in a larger space. This Mi2 is operating on a smaller space. So for a fair comparison, for a valid comparison, we have to project them on the same subspace. And these matrices, Pi2, they are doing that projection in a smaller space. And in the smaller space, you should have this inequality to be true. Okay. So again, just to recap, this captures which mechanism is sharing less information, and this captures which mechanism is having less error covariance, which is having more error covariance. Right. Now it turns out that to guarantee this condition, remember this error covariances depend on the noises, right? So if the noise added by Mi2, which is this, is larger than the noise added by the first mechanism, if you can ensure this, then this condition is automatically ensured. This is a sufficient condition for guaranteeing this condition. Okay, so now we need to do one more thing for this privacy. Okay, before that, this is an important or an interesting result for these particular privacy mechanisms. It says that, let's say you start with some normal measurements, you implement one privacy mechanism, and now you take the output of this privacy mechanism and you further limit the information. You superimpose another privacy mechanism on top of this first privacy mechanism. Now this result says that this Mi2 will always be more private than Mi1. So in some sense, you must be familiar with the data processing inequality in information theory, right? If you process information even more, you cannot improve on the information if you process the signals more. So similarly, if you take an output of the first privacy mechanism and if you further process it, then the privacy can only increase, it cannot decrease. Okay, so this is one sort of interesting result that is specific to our definitions of the privacy mechanism. Okay, so that was all about the first question. Now let's move on to the second question. How do we detect attacks in the system? So for that, again, we have two different types of measurements. We have a local measurements, which is YL, and we have the received measurements. So remember, we have interconnected system, right? So if you look at one particular agent, you will have some local measurements, and there will be some external measurements provided by the other agents. Okay, so that is this received measurements from other agents. And the goal is to detect attacks using both of these local measurements as well as the received measurements. And this was the pitch that I presented earlier, right? If you share information, then you should be able to detect attacks in a better sense. Okay. So in this case, we are using not only local information, but also the external information. And we'll use both to detect attacks. Yes. Yeah, so that is in, yeah, so via it contains. Yes. So the agent will take its local information, it will process it using the privacy mechanism and then share it. Okay, so again, we fall back to the previous scenario, as I mentioned that. So for this, remember, okay, let me go back to mention one more point. So here the goal is to detect this attack A. Okay, so here A denotes the attack, this V is the noise, and we have this signal X of minus I. Now this X of minus I is not known. Okay, so it acts kind of a nuisance parameter. If this Xi was not there, then we could have directly proceeded with detecting this attack using the standard procedure. Okay, but now the challenge is we don't know what this x minus I is. What is x of minus I? It is the state of all the remaining agents. So a local agent does not know what is the state of the external agents. So now the question is, if we don't know this x of minus I, how can we do attack detection? Okay, so for that, we again decompose this x of minus I into two different parts. Okay, so here this first part is, we can estimate this first part, this first component. How do we estimate this component? Using this received measurements. So remember, this YR contains this x of minus I. Okay, so this x of minus I can be estimated using this YR, but only this portion can be estimated. This remaining portion cannot be estimated. So if we cannot estimate it, we somehow try to eliminate it. And we eliminate it by pre-multiplying this whole thing by such matrix M such that this M transpose times this matrix becomes 0. So essentially we are eliminating this part because we cannot estimate it. So this is what we call as processing of measurements. So we process the measurements in two ways. The first way is estimating what the first part, which indeed can be estimated. The second step is to eliminate the part which cannot be estimated. And once we do both these steps, we get this final equation. So you can forget about this part, but Z equal to this M transpose FAA plus VP. And you notice that there is no X of minus I in this case. So now using this Z, we can directly try to estimate whether this attack A is present or not. Okay, so this is the processed measurement. And again, we know what this M is, we know what this F of A is. We also know what this V of P is. We know the statistics of this V of P. So now we can use a standard binary hypothesis testing framework to detect the attacks. So again, we have two hypotheses. A is 0, attack absent, versus A not equal to 0. And we use the generalized likelihood ratio test to come up with this test. Again, this is a standard theory. There is nothing conceptually new here. Okay, so this is the final test that we have. And then we have some results. We can indeed find the performance of this test. So for that, first we need to find the performance of this test statistics T of Z, and we can show that it has distribution of chi-square under H0 and a non-central chi-square under H1. Okay, where Q is this parameter. Now here there are two important parameters that come into play. One is this Q parameters. It represents the degrees of freedom. In some sense, it represents the number of measurements. If your number of measurements are larger, then Q is larger. Okay? And the second parameter is lambda. This lambda represents the energy in the attack signal. Okay, so you have the energy in the attack signal, and you have the number of measurements that are available to you for performing the attack detection. So naturally, if the energy in the signal is larger, then you should be able to detect in a much easier fashion. Similarly, if this Q is larger, meaning that you have more measurements, then again, you should be able to do a better attack detection in those cases. So to define the performance of the test, we compute the detection probability. And again, we can do this using the standard tail probabilities of the chi-square random variables. And here is the result. Now, this is a counterintuitive result. Why it is counterintuitive? Let me explain. So if you look at the first plot, on the x-axis, we have Q, and on the y-axis, we have the detection probability. Now here what it says is that as Q increases, PD is decreasing. Okay, so remember what Q is. Q is the degrees of freedom or the number of measurements. Okay, so ideally if you have more measurements, that means you have more information, and more information should help you in detecting attacks more. Okay, but this is the exact opposite. If you have more information, your detection probability is decreasing. Okay, so this is a counterintuitive result, and I'll explain. Okay, it's here. Why is it like that? Because this likelihood ratio test is not an optimal test. And in this case, there is no uniformly optimal test that exists. So if you're familiar with estimation detection theory, it's there is no uniformly optimal test. Okay, so some tests might perform better in some regions, other tests might perform better in some other regions. Because of that, we are getting this counterintuitive behavior. Okay, but the behavior with respect to lambda is what we expected. If lambda is increasing, PD will increase, which you can clearly see in these curves. Okay, so now I'll tie the two results up. This is the final question. So is there a trade-off between security and privacy? Okay. So here is a direct result. So let me parse what this result says. So first of all, does increasing privacy always reduce detection performance? The answer is no. Okay, so the trade-off is not strict in this case. So what it says is that if you consider two different privacy mechanisms, M2 and M1, then Q1 will be larger than Q2 and lambda 1 will be larger than lambda 2. Okay, so this means that the lambda value will increase and Q value will also increase. But we have already seen that this PD is decreasing in Q and increasing in lambda. Okay, so that if you combine these two results, that means that the difference in the detection probability, they can be either positive or negative. That means that the trade-off is not strict. If you have a more private mechanism, the detection performance can be lower or it can be higher. So again, a simple example to show that. So here we have two different privacy mechanisms. In the first mechanism, there is no privacy. Okay, so the selection matrix is identity. We are adding no noises. All right, so there is no privacy. In the second mechanism, we have some selection matrix and we are also adding some noise here. Okay, so we are implementing privacy. And these are the parameters. So if you look at this plot, in this region, the detection performance of case 0 will be larger than case 1, meaning that a less private mechanism will correspond to a higher detection probability. But in this red region, we'll have the reverse case. So in some cases, we will have a trade-off. In some cases, we won't have a trade-off. And the fundamental reason behind this is that we were using this GLRT, which is not uniformly optimal. Because of that reason, we are getting this non-strict trade-off in this case. But we have some special case, and the special case is this, that there is a strict trade-off if you only add noise. Okay, so if the selection matrices are the same, okay, and you just have more privacy due to more noise, in that case, we will have a strict trade-off in this case. So just to conclude, we proposed a new mechanism to limit these shared measurements. And then we had this counterintuitive result that this trade-off is not strict in general. So in the first part of the talk, we had seen that the trade-off is strict, but in this case, the trade-off is not strict. In some cases, you might have a trade-off. In some cases, you might not have a trade-off. And then we have once sufficient condition for a strict trade-off. So essentially, the whole, the final message that I want to give is that whenever you are implementing security and privacy in these systems, we need to be a bit more careful because there is a connection between these two. And we need to be aware of these connections. And we need to see how much level of privacy we want. And correspondingly, the level of security might reduce. Okay. So as system operators, we should be familiar with these trade-offs and design systems in a more wholesome manner. Okay. So I'll leave it at again this slide, and thank you very much. Are there any online questions or?
So thank you, Professor, for such an information talk. If you have any questions, you can ask.
Hello. Security is viewed as not exposing the attacker, and the attacker can hide behind some phenomenon that's happening there. Now, if I was to look at signal processing on networks, where there is information flow through the network, like in a CPS, and the information has to be processed to make some decision. But the information has to remain private. So what does all this have to say about that? Does it mean that if you want to keep the information private, your signal processing will suffer?
Yes, definitely. So in that case, again, we have a trade-off, right? Because if you want to implement privacy, then again, you will share inaccurate information or less information. And whatever thing you need to do with that information. Here, the thing was that we want to detect attacks based on that information. But if you want to do some other processing, let's say you want to do some machine learning or some other processing, that performance will suffer. Yeah. So that trade-off is valid in those cases.
And there's no way around it. I mean, you cannot sort of achieve both privacy and good signal processing.
So in that sense, the fundamental is this trade-off is fundamental. You cannot bypass that.
Any other question?
It wasn't very clear what information is shared with the attacker, let's say in the second problem.
So we are not sharing information with the attacker.
No.
We are sharing information between different subsystems.
Yes. But if you explicitly model sharing of information with the attacker also, then does this trade-off still hold, in the sense that if you have more privacy, then you have less security?
So if you share more information with the attacker, that won't help the attacker in some sense.
Why not?
Because so we assume that the attacker already knows the system model.
Yeah.
So it knows ABCD, right? Those parameters it knows. And based on that, it has somehow designed the attack signal. Now, the attacker has injected the attack signal. And then if you share the outputs with the attacker, in this setting, I don't think attacker can do, maybe it can design the attacks more intelligently.
Yeah.
But that is not what we are considering here. Here we are considering any general attack signal.
Yeah.
So if that is the objective of the attacker, then in that case, what you said will come into picture.
Yes, I mean, if the goal of the attacker is to divert the state to a certain other desired state of its desired state, then it helps to know the initial state, right? For example, so
Correct.
sharing more information with the attacker then also leads to more loss of security in some sense.
Right. So in that sense, so in that case, if you are sharing information with the neighboring agents, then you are saying the attacker can also tap into that information.
Yes, potentially. Yeah.
Right.
And then we might not see this trade-off, right? In the sense that we may lose more privacy, but at the same time also at the same time also lose security. That may also be possible,
No,
right?
this will happen because again, if you are sharing inaccurate data
Yeah.
with the attacker, then the attacker might not be able to do that much with that inaccurate information.
Right.
So I suppose the trade-off will still hold.
Okay. And the other question I have is, so here you're just caring about detecting the attack, right? And you're not really caring about resilience to the attack or the impact of the attack, right? So there could be an attack which has very minimal impact on the system state, let's say, right? So in particular, in the second problem, you were also considering noise, right? So compared to the noise, let's say the attack signal is very small, right? So then there is an attack, but then we might not care about it, right? We might, yeah. So does it help to think in terms of resilience and then maybe look at these kind of questions?
So resilience, by resilience, you mean the system is inherently resilient to the effect of those attacks?
Or maybe I should put it in the sense that what is the impact of the attack signal on the state?
Right.
Right.
Right. Yeah. So again, as you said, the attacker might want to take the state to some unstable region, or again, in estimation problems, the goal is to increase the estimation error of such attacks. Yeah. So if we consider those performance matrices, there might be some results that are different from here, but we'll have to look into this. I cannot say for sure that the trade-off will stay, but those are valid settings.
Any other question? So thank you, Professor, for
Thank you.
session. And we have arranged the refreshment at the coffee hut, and you can continue our talk with Professor at the coffee hut. And thank you and great evening.